This video hopefully will help you with your shear force and bending moment diagrams. If it doesn't, perhaps you need to find these people.
In 1972, a crack commando unit was sent to prison by a military court for a crime they didn't commit. These men promptly escaped from a maximum security stockade to the Los Angeles underground. Today, still wanted by the government, they survive as soldiers of fortune. If you have a problem, if no one else can help, and if you can find them, maybe you can hire the A-Team.
Anyway, enough of that. They're available to watch all of them A-Team stuff. Amazing. Anyway, shear force bending moment diagrams. You will get one in an assignment where you've got to draw shear force and bending moments. So we'll go through it. We've done a few in class, so yeah, all the same type of procedure. So here's my beam, 6 kilonewtons there, 3 kilonewtons there, 7 kilonewtons, 3, 9, 13, and the beam is 15 meters long. It's got a UDL of 0.5 kilonewtons per meter. So we need to draw the shear force and bending moment diagram for that beam. First of all, you've got to convert the UDL into a point load, because we need to take moments in a bit to work out this reaction and this reaction. So point load, point load, point load, UDL. To convert that into a point load, we've got to convert it by the length it acts over. So in this case, it's 15 meters and it's 0.5 kilonewton per meter. So to make it into a point load, you multiply that by 15, because it's 15 meters. So 0.5, 0.5, 10 to the 3 equals that, times by 15 meters gives us 7.5 kilonewtons. So that's converted that into a point load, and as we know, that point load is going to act halfway along the beam. So there's 15 there, so about halfway along we're going to have a force now of 7.5. That represents the UDL, the uniformly distributed load, which you could say is the weight of the beam. So we'll have 1, 2, 3, 4 forces now. So there it is. The 7.5 kilonewtons acts halfway along the beam. So the beam is 15 meters, so it's 7.5 halfway. So now we've got a force there, force there, force there, force there. It makes it easier for us now to work out the bending moment, but first of all we've got to do the reactions. So you should be fairly comfortable in doing this. Assume moments are 0, some of the moments are equal to 0. The sum of the forces are 0. The beam is in balance or equilibrium. We'll call clockwise moments positive, anti-clockwise moments negative. And a moment is a force times distance. Moments about point A. So I'm calling that point. Right, yeah. So there's point A. take moments about that point. So 6 times by whatever it is, let's go up here and look at it. So we've got 6 times by 3, 7.5 times by 7.5, 3 times by 9, and 7 times by 13. All going clockwise, so it's going to be positive. So that's point A, pivot point A. So I'll scroll down. So there's my force times distance, 6 times by 3, 6 times by 3. It's going positive, hence that. That's my UDL at 7.5 meters away. 7.5 at 7.5 meters away. All going that way, because that's our pivot point, all going anti-clockwise. Sorry, clockwise. Plus 3 times 9, 3 force 9 meters away, 3 times 9, it's going positive, hence we've got positive. The last one of the forces, 7 times by 3, there's my 7, sorry, 13 meters away. Again, it's going positive, so 7 times 13 is a positive moment. So there's that 1, 2, 3, 4 forces, and the last one is RB, which we need to find. So RB is there, coming up. It's 15 meters away, and it's trying to go anti-clockwise, and we call anti-clockwise negative in this case. Hence why I got that. So there's all my forces, all got to equal 0. So work that out, gives you, right, do it in a bracket, 6 times by 3 plus 7.5 times by 7.5 plus 3 times 9, 3 times 9 plus 7 times 13. All equals 192.25 minus RB by 15. Leave that there. Take this negative term over there to make it a bit easier. And then I'm going to bring the 15 down. So divide all of this by 15. That will give us RB. So divide that by 15. 12.81 kilonewtons. Don't forget, these forces are a killer, so make sure you put it back in. So RB is 12.8, which means there's 12.8 coming up there. We now need to find RA. Now we know that the sum of the forces equals 0, which means RA and RB are coming up, and all these forces are coming down. So there's reaction there and a reaction there. They're going up. So that plus that has got to equal that plus that plus that plus that, because our beam is in balance. So RA plus RB has got to equal 6 plus 7.5 plus 3 plus 7. Add all of them up, and you should get this. 6 plus 7.5 plus 3 plus 7. 23.5. So there's 23.5 coming down, which means there's got to be 23.5 coming up. So these two are coming up. We already know what RB is, so we can use that. So bring the RB over here. So RA 23.5 take away RB, because that plus that has got to equal that. So if I take RB away from that, it's going to give me RA. And we know what RB is because it's there. So 23.5 take away 12.82 will give us what RA is. Don't forget to put the killer back in. 10.68 kilonewtons, because these are all killers. So make sure you put it back in. So just to check that we know that that plus that has got to equal 23.5, just to make sure. So 10.68 plus 12.82 has got to equal 23.5, which it does. So for 10.68 plus 12.82 will give us 23.5. So we know the reactions. So we know we've got a force there, and a force there. And we've got a UDL still there. And now we know the reactions. Don't forget, when you're doing a UDL, you've got to keep it in for the shear forces and for the bending moment. When you're looking at reactions, you can convert it into a point load to make it easier. But when you're doing a shear force and the bending moment, you've got to put it back as a UDL. Let's do a gin. Shear force diagrams, don't forget, all we're looking at now is the forces coming up and the forces coming down. So we're not doing bending moments, we're doing shear force, so it's just forces up and forces down. So like we did in class, I'm going to start from this side. I'll start from here and we'll work this way. So whatever we see is what we include. So I'll start off from the left, x equals 0. What force can I see at x equals 0? All I can see is this 10.68. So I'm starting off at x equals 0. Ignore this for now. X equals 0. All I can see is 10.68. That's my first point. I'll then come in x equals 2. So all I can see at x equals 2, which is here somewhere. All I can see is that force coming up, and I can see 2 meters worth of this UDL. So I see 2 meters worth of the UDL. The UDL is 0.5, and we're 2 meters in, so 10.68 coming up, and the UDL 2 meters worth is coming down. Don't forget the kilonewton. So I've got 10.68 coming up, 10.68 coming up, and I've got coming down 2 meters worth of my UDL, which is 0.5 kilonewton per meter. That gives me 9.68 kilonewtons. So the shear force at that point here is 9.68. And now I'm going to go to x equals 3. Right, we're going to have 2 points at x equals 3 because we've got a force at x equals 3. There's my force coming down. I'll rub this out. So at x equals 3, I'm here. So I'm there. So I can see now this force coming up, 10.68 coming up. I can see 3 meters worth of this UDL. And I can see that force there. So there's 2 points here, first of all. So we'll do 10.68, that's the force coming up. 3 meters worth of my UDL. So 10.68 coming up. Coming down, I've got 3 meters worth of my 0.5 UDL. Gives me 9.18 kilonewtons. And then, that's 1 point I plot on my graph, but I've also got, right, the 6 kilonewtons coming down. So make sure you have 2 points when you've got point load. I got 9.18, it's going to be 1 point, but I've also got the 6 kilonewtons coming straight down. So I'm going to take away the 6, gives me 3.18. So on my graph, I'm going to have this. I'm going to have, with the UDL, we have straight lines coming down, sloping line, and then the UDL kicks in, sorry, the point load kicks in straight down. That's why we've got 2 points. We've got that point, and that point. 2 points. So carry on down. I've gone to x equals 5. So at x equals 5, I can see, let's get rid of that, x equals 5, which is about here somewhere, there. I've got this coming up, I've got the 6 coming down, and I've got 5 meters worth of my UDL. So that's my force coming up. 5 meters worth of my UDL and my 6 kilonewtons point load coming down. Okay, don't forget I've taken the kilonewtons off, right, but I put it back on, so make sure you put it back on. So at that point I've got 10.68. Coming down, I've got 5 meters worth of my 0.5. And I've also got my point load coming down, so I'll take that away as well. Gives me a shear stress at that point, 2.18 kilonewtons. So at x equals 5, that's what I've got. I've got shear stress of 2.18. I'm now going to go to, what have I gone to? I've gone to 7. So I'm now, get rid of that. It's 9 meters to there, so I'm here somewhere. So 7 meters in, I've got this force coming up, that force coming down, and now I've got 7 meters worth of that UDL. I'm only looking what I can see here. That force coming up, that force coming down, and 7 meters worth of my UDL. So 10.68 coming up, 7 meters worth of the 0.5 coming down, and also the 6 coming down. So on a calculator, 10.68, take away 7 meters worth of my 0.5, take away my 6, gives me 1.18 kilonewtons coming down. So here I've got 7.18 coming down. So 1.18 kilonewtons at 7 meters in. I've gone to x equals 9 now, and as before I've got a force at x equals 9, so there's going to be 2 points again. Alright, so at x equals 9, get rid of all of this here. So I've got this force coming up, because I'm here now, x equals 9. I'm just looking what I can see. I can see that force coming up, this force coming down. I've got all of this UDL. I've got 9 meters worth of the UDL. And I've also got this 3 kilonewtons coming down. So I'm going to have 2 points again like I did before. I'm going to have a point like that and a point like that. It'll slope down for the UDL, and then the 3 kilonewtons will kick straight down. So x equals 9, that's my force coming up, 9 meters worth of the 0.5, and the 6 coming down. So 10.68, take away 9 meters worth of my 0.5, take away my 6, 0.18, so that's 1 point. So make sure you plot that, 0.18 kilonewtons. I forgot to put the kilo. So that's that point there, for example, and then I've got the 3 kilonewtons to bring it straight down like that, because 3 kilonewtons kicks in there, look. So 0.18, also the 3, so take away the 3, gives me 2.82. So we've got 2.82 kilonewtons. So that point and that point. Minus, don't forget. So we're going down now below this axis, which tells us where the minimum shear force is, or zero shear force, which is an important point. I've now gone x equals 11, so at x equals 11, I'm here somewhere. X equals 11, I'm here. So there somewhere. I can see that this coming up, this coming down, this coming down, and I've got all of this 11 meters worth of my UDL. So x equals 11, I've got the force coming up, this is my 11 meters worth of my UDL. Point load coming down, point load coming down. So calculator, 10.68. Take away my 11 meters worth of my 0.5. Take away 6, take away 3. 3.82 kilonewtons. So it's a minus number, don't forget it. So that's my point at x equals 11. And now I've gone to x equals 13. At x equals 13 as before, I've got another point load kicking in. So we're going to have 2 points. So let's get rid of that. So at x equals 13, I've got all of this because I'm x equals 13 now. So I've got that force coming up, coming down, coming down, coming down, and I've got 13 meters worth of my UDL. So we'll have 2 points like we did before, point like that and a point like that. X equals 13, that's my force coming up, 13 meters of my UDL, point load coming down, point load coming down. So just calculate it. Take away 13 meters of my 0.5. Take away 6, take away 3, gives me 4.82 kilonewtons. But don't forget, we've also got this 7 kicking in. So if I go up, 7 kicks in as well. So we've got 2 points. Where was I? There. So we've got 4.82 minus, and also the 7 kicks in. So take away 7. Gives me 11.82. So we've got that point and that point. 2 points on the graph. The last one, x equals 15. Don't forget this beam is in balance, so we would expect it to come back to 0 at x equals 15. So at x equals 15, we've got this force coming up, this 6, this 3, this 7, and I've also got the entire length of the beam, so we've got 15 meters worth of the UDL. So we've got 15 meters worth of the UDL here, 15 meters of it, so all of this. We've got that, and we've also got this force here kicking in, so we'll get 2 points again really, and hopefully it comes back to 0. So with that force coming up, coming down, coming down, coming down, 15 meters worth of the UDL coming down, and 12.8 of that force coming up. So 10.68 coming up, 15 meters worth of my UDL. I'm doing colour. 10.68 coming up, 15 meters of my UDL coming down, point load, point load, point load. Gives me that. So just to make sure, 10.68. Take away 15 meters of the 0.5. Take away 6. Take away 3. Take away 7. Gives me minus something, 12.82. So that's 1 point. And then don't forget, we've also got this force here coming up. So he's coming up. So we're going to add it. And like I say, hopefully it comes back to 0 because the beam's in balance. So at the end it should be 0. So that's my 12.82 coming in. Looks good because we've got a minus there and a plus there. You'll always know you're correct if when you get to the end of the beam that this point here is equal to that plus. So we've got that point, and we've also got a plus 12.82 coming in, which gives me 0. Everyone's winner. So that's the shear force calculations at these points. So I've gone, try and go as many points as you can, but make sure you go, I would really go where there's definitely point loads. So we've got 2 points there, we've got 2 points there, and we've got 2 points there, and we've got 2 points there in theory. And plot your graph on a bit of graph paper. There we go. So there's all my plots. Don't forget a UDL. So it starts off straight up. Ding 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 ding. Right, that's the reaction, 10.68. Then the UDL kicks in, sloping line. Then the point load 6 newtons comes down. That's why you got 2 points. That point and that point. Don't go straight to that point. There's a point there, UDL sloping, 6 kicks in. Then the UDL carries on until the 3 kicks in. 2 points. The UDL then kicks in again, UDL. Then my 7 kicks in straight down, 2 points, point there and a point there. So the 7 kicks in. Then the UDL comes at the end, towards the end, UDL, point there. And then the reaction kicks in, brings it back all the way to 0. So that's your shear force diagram. I would label this point here because at this point it's crossed 0. So 0 shear force at 9 meters from the left. So where there's 0 shear force, there's maximum bending moment. So when we draw a bending moment diagram, hopefully the top of the curve is going to be at x equals 9, because that's where 0 shear force, maximum bending. So at that point, that is most likely to be the point of fracture, because you've got the biggest bending moment there. So the next bit is to work out our bending moment calculations. So go back to our beam again. So we've got all our forces, and we've got UDL, and we've got reactions. So I've gone to the same x equals 0, 2, 3, 5, 7, 9, 11, 13, 15 as before. It's up to you, but I would try and stick it to the same. Make sure you go where there's a point load. And one thing you need to remind, a moment is a force times a distance. Again, we're starting from the left, so whatever moment we see at certain points, that's all we look at. And when you're doing a bending moment diagram, you need to use that little term there, wx squared over 2, where w is whatever the UDL is, and in our case it's 0.5. That doesn't change, so that always stays the same. It'd be 0.5. X squared is how far we've come in, the distance, and 2 will always be 2. So the only thing that's changing is the x. X equals 0, x equals 2, x equals 3. So the w in this case is 0.5. That doesn't change, and the x changes. So I've gone in, x equals 0, that point there, all I can see is the moment produced by this. Force times distance. X equals 0, so my moment is force times distance, 0. Because you can't have a moment unless you've got a distance, and I haven't got a distance yet. So I see the force, but it's not creating a moment because it's just pushing up against 0. I've now come in 2 meters. At 2 meters, which is about here somewhere, I can see the moment due to this force going that way, and I can also see the moment produced by the UDL. So I've got 10.68 times by 2. That's the moment produced by that. And I've got this wx squared. This is the moment produced by the UDL, wx squared over 2. So w is the 0.5, and the 2 is the x, which is there. Squared is squared over 2. So put that in the calculator. 0.5 times by 2 squared, divide by 2, gives me 1. So 10.68 times by 2, take away 1, gives me a bending moment at that point of 20 point, what's gone wrong there? 0.5 times by 2 squared equals that, divided by 2, yeah, 1. Then I've got 10.68 times by 2, yeah, equals that. Take away 1. Something wrong here. $20.36. Oh dear, dear, dear. Looks like there's a mistake there, look. Let's just do that again. Yeah, there's a mistake there. Well done, Morg. Brilliant. 2 squared equals that, times by 0.5 equals that, 2, divided by 2 equals that, 1. Ooh, do. Should have checked my calculations. There's a lesson there, look, check your calculations. 10.68 times by 2. Take away all of that, 1. 20.36, naughty. Make sure. Right, so this now is wrong. Hang on. 20.36. So that should be 20 there, look. Hopefully I haven't made that mistake all the way through. Right, so that's the bending moment at that point. I've now gone to x equals 3. Alright, let's hope I haven't made the same mistake. Always check. X equals 3 is there, look. So it's the bending moment. I've got the moment due to this force times 3. I've got the UDL, and I've got this, although because I'm right underneath it, there's no moment produced by it, so we'll ignore that. So that's my reaction. Am I 3 meters in? That's my UDL, WX squared over 2. All that's changed is the 3. All that's changed is the 3 and 3, because the 0.5 is the same. The 0.5 is that. 3 meters in, so let's just check now. Obviously that's 6 times, there is a force there, but because I'm directly below it, there's no moment, because there's no distance. I'm directly below it, so you can put it in, but it's up to you. But it is there, but it's not creating a moment. So let's see, right, and let's do that just slowly now. So 0.5 times by 3 squared divided by 2 gives me 2.25. Obviously you can keep it in your calculator, you haven't got to do it like this. 2.25, 2.25 there. Right, quick if you just do all in one go. 10.68 times by 3 gives me that. Take away 2.25. Let's see, I hope I made the same mistake. 29.79. Normal service resumes. So the bending moment at x equals 3 is 29.79. So I'll carry on now. X equals 5 here somewhere. So I've got the bending moment produced by that. I've got the bending moment produced by that, because now I've compassed it. I've compassed it now. So there's a bending moment, and I've got the UDL bending moment. So x equals 5, 10.68 times by 5. That's my UDL. That. That's my UDL. All it changes is the 5, don't forget. So that's the same, that's the same, that's the same, that's the same. All is changing is this number here. And now we're 2 meters past the 6, so that kicks in. So 5 squared times by 5, 0.5, sorry. So 5 squared, 0.5 equals that. Divided by 2 gives me that. 6.25. 6.25. So 10.68 times by 5 equals that. Take away 6.25 equals that. Take away 6 times 2, which is 12. Press equals 35.15. So that there is the bending moment at that point. X equals 5. I then got to x equals 7. So here somewhere. So I've still got the bending moment produced by that force, and my UDL. So x equals 5. So really we're just going up now, up by 2 meters, up by 2 meters, up by 2 meters. Going up by 2. So just increase these by 2 now. So 10.68 times by 7, that's my UDL bit, and that's my moment due to that 6 times by the 4. So I'll work him out again, just to go the long way. You haven't got to do it like this. Just make sure you square the 7. Don't square it all. Divide it all by 2. Gives me 12.25. That's the moment produced by the UDL. So 10.68 times by 7. Take away 12.25. Take away 6 times by 4. 6 times by 4 gives me 38.51 kilonewtons per meter. Don't forget the killer. That's the bending moment at that point. And my next point is 9. Make sure now you go to 9, because from our graph, our shear force graph, playing up again, we know that it goes across 0 at 9. So we're expecting this to be the biggest bending moment. Where there's 0 shear force, which is there's maximum bending. So the top of our curve. So hopefully, whatever number we get, when we go further along, the number should be coming down back to 0. So once you've found the maximum bending moment, that's the important point. So x equals 9. So I've got here, I'm here. That moment produced by that force, that moment produced by that force, all of this UDL. That 3 there doesn't really affect because I'm directly below it, so there's no distance, so it's 0. But hopefully it's going to be our biggest number because it's the position of 0 shear force, which should be our maximum bending. So that's that one, 10.68. That's my UDL. That's my 6. And that's my 3. I've kept it in, but really, because we're below it, there's no moment, so the distance is 0. Again, we're going up by 2, look, so everything goes up by 2. Everything goes up by 2. Everything goes up by 2. So I put that in at 3, but there's no moment produced by it, so you haven't got to put it in. Work that out any way you want. I'll do it this way again, times by 0.5. Make sure you just square the 0.9, divide that by 2. It gives us a number, 20.25. So work it out. Hopefully it's our biggest number because it's the position of 0 shear force. maximum bending moment. So stick it in, calculator, 6 times by 6, 36. All right, I'll leave that out for now. Gives me 39.87. So 39.87 kilonewtons per meter. So hopefully that's our biggest number. That's the position of zero shear force. So it should be our biggest bending moment there. So if everything's correct, this is where the biggest bending moment's going to be, which means it may fail there due to bending. So we'll carry on. I've gone to x equals 11. So going up by 2 again. Up by 2, up by 2, up by 2, up by 2. Don't forget the 3 kicks in now. So at x equals 11, x equals 11 here somewhere. 13's there, 11's there. So we've got moment due to that, moment due to this, moment due to this, and the moment due to that UDL. Hopefully it's coming down because this point should be our biggest bending moment. So that's the due to that 10.68. There's my UDL, that's my 6, and there's my 3. All that's happening is that's going up by 2, that's going up by 2, which means 911, 911, up by 2, up by 2. Work all it out, and you should get that. 11 squared times by 0.5 equals that, divided by 2 equals, let's do it again, 11 squared times by 0.5 equals that, divided by 2 gives me 30.25. Right. So work that out, 10.68 times 11, take away 30.25, you can go quicker than me if you want to, take away 6 times 8, 6 times by 8, take away 3 times by 2, right, do that now if you want to, equals, where are we? 13. Don't forget we have got the 7. We have got the 7. Hang on, what's going on there? Sorry, 11. Ignore that. So 3 times by 2 equals that 33.32. So it's coming down because obviously that is the maximum bending moment. So it's coming down now, which is good. Which means we know that's the important point. So really, once you've found that important point and you're confident and they're coming down, right? So I've done a few more points because just for a laugh. At x equals 15, it should come back to 0. So I would do that, but I've gone to x equals 13. Again, all's going up by, we've gone up by 2, which means these are going up by 2, up by 2, up by 2, up by 2. We have got the 7, but because we're directly below it, as before, there's no force, there's no moment, because we're directly below it. No internet. Ooh. We're directly below it, so there's no moment produced. So that's my x equals 13. I got 13, that's the moment, 10.68, 13 meters away. That's my UDL. That's the same, that goes up by 2. Right, 13, 13. This goes up by 2 because now we're 10 meters away. This goes up by 2 because we're 4 meters away. The 7 is there, but there's no distance, so I put it in, but it's a 0 really. So all that, right, so 13 squared times by 0.5 gives me that, divide that by 2, gives me 42.25. Obviously you can stick it all in one, go in a calculator. Right, I'm just going slowly. 10.68 divided by 13, because you don't want to make a mistake in the calculator, because this is all correct. You just don't want to put it in here incorrectly. Take away 42.25. Take away 6 times 10, 60. Take away 3 times by 4, 12. Ignore that because there's no distance. So 7 times by 0 is 0. So plus equals, and you get 24.59. So it's coming down still, which is good. That's our high point. It's coming down, so we're getting close to 0, which is good. Don't forget it is killer. The last bit, x equals 15. So all the way to the end, the beam's in equilibrium. So hopefully our number will become 0. We have rounded these up a bit, so we may not get exactly 0, right? Because we've rounded up, but it should be fairly close to 0. I mean, if we get a massive number, there's something wrong. So we've got that force in that moment, 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 and all of this. That is there, but because we're directly here, it's times by 0 again, so there's no moment produced. So that's my force moment, UDL, the 6, the 3, and the 7. Again, up by 2, gone up by 2, gone up by 2, gone up by 2, gone up by 2. That's my 7, gone up by 2. Don't forget, that reaction is coming up. So the force is there, but because we're directly below it, there's no moment. So don't include it really. I put it in there just to show you. So it's coming up, but because we're directly there, there's no moment produced by that force about that point. So put it all in, you should get 0. I get very close to 0, but because we've got a rounding error due to this, right, but it's very small. If you get a big number, there's something wrong. So your reactions could be incorrect. So 15 squared, let's do it again, times by 0.5 equals that. Divide by 2. Gives me a number, 56.25. 56.25. Put all that in. 10.68 divided by 15. Take away 56.25. Take away 6 divided by 12. Take away 3 divided by 6. 3 divided by 6. Take away 7 times by 2. 14. That there, look, so you could include it, but that times that is going to be 0, so I'll ignore that. Equals. So obviously it doesn't come exactly to 0 because we've rounded these here up. That 10.68 reaction was rounded up earlier on, so it's very close to 0, so I'll take that. So it's come back to 0, which we like because simply supported beam, it should do that. Start 0, end 0, which it does. So that's our points. Obviously the K's are there. You haven't got to put the K's in on your graph, but just make aware that it is kilonewtons. X equals 9. Right, that's worked out. So we know that at X equals 9, 0 shear force, maximum bending moment. So that's worked out. So maximum, that's the biggest number we got. Comes back to 0. Plot your graph. Obviously that point there with me is slightly out because of my error up there. So always check your numbers. but the rest are correct. This is the most important point. That's the most important point there, because it's the maximum bending moment. 9 meters from the left, that's where the maximum bending moment of that is, and that is where it could fail. It's going to most likely fail there due to bending. So at x equals 9 is our maximum bending moment. Then it comes back down to 0. Plot your graph, label your axes. So that is the maximum bending moment at x equals 9 from the left. So that's where failure is likely to happen. Maximum bending moment. I won't put any rivets there or any joints, because that's where maximum bending is. So hopefully that's a bit clearer. You will have to do one of these in your assignment. This will be a past question. Your merit one is a overhang. It's the same process as we've done. It's just that your graph may do this, your bending graph will do that. So you've got to, it's the same process, don't be scared, but with an overhang you'll get a graph going over like that, and this is the point of contraflecture. That point there is where it goes from positive to negative, and that's called the point of contraflecture. So you'll need to identify that in your merit question. But it's the same process as we've done. Just with the overhang, you'll get it going over like that, or something like that. So you obviously got 2 points of maximum bending moment there. So go through the question, check your numbers. I made a mistake there, just check your numbers all the time, and hopefully that will help you. If it doesn't help you, phone the A-team. No star.